Richard back to give us more on coherent sheaves.
Okay, so I totted up the votes, which were all entirely for, much to my surprise. They were basically all saying, please do lots of ext computations and technical. I'm not joking. So I'm quite impressed. I guess lots of people are really working with reflexive sheaves and coherent sheaves, and they really want to know. So the people who actually spoke and actually expressed a preference really wanted to see how you work with these sheaves, do examples, do computations, and see some deformations of sheaves and so on. So I apologize to those of you who wanted to relax and hear about, I don't know, some nice talk about curve counting or something, which would have been my preference because I could have just put up the slides and gone to sleep. But I actually had to prepare a talk. So yeah, this is going to be sheafy. So, but at least it gives me the opportunity to do a better job of that example that I rushed through last time and explain. People basically were asking for homological algebra. So I'm going to re-explain this set construction using homological algebra, so the way an algebraic geometer would do it, and go from there. All right, so last time we had this kind of hierarchy of, we had these examples of sheaves, which sort of, this hierarchy goes up in levels of singularity. So we had these torsion sheaves. So these are the kind of worst in some sense, the most singular. So e.g. the structure sheaf of some subvariety. Okay. So these are torsion. That means that, remember, everything's an OX module, so you can multiply by functions. And these are killed by certain functions. So these are killed by the ideal sheaf of Z, so the functions vanishing on Z. So that's what torsion means. Okay, and then sort of better are things that like torsion-free sheaves. So e.g. the ideal sheaf of Z. All right, and these are more relevant to gauge. There are gauge theories which use torsion sheaves, but these are more relevant to gauge theories. So in particular, these will model the bubbles in Donaldson theory and the codimension 4, real codimension 4 bubbles in higher dimensional gauge theory. But we'll come to that. Okay, and then the next up is reflexive. So what does this mean? So torsion-free means that, so if E is torsion-free, this implies that E injects into its double dual. All right, so its dual means you take HOMS to OX, and then the double dual, you do it again. Okay, so you think that might be something like E. If you do it here, you get 0, right? The HOMS from OZ to OX are just 0, because this is torsion and this is torsion-free. So the image of some torsion would have to be torsion in here, and there's no torsion in here, right? So if you think of a map going from here to here, let's see what 1 goes to. Well, whatever 1 maps to, it has to be killed. If I pick some F in the ideal sheaf of Z, then this is a map of OX modules. So whatever 1 maps to, let's call it E, then F times 1 must map to F times E, where F is anything in the ideal sheaf of Z. All right? So linearity gives you this, but this is 0. Okay, so this has to be 0. All right, but so E has to be killed by F. It has to be torsion, but there is no torsion in functions on X for X is smooth variety, or indeed an irreducible variety. So, or yes. So this implies that E is 0. Okay, so this whole any such HOM is 0. So torsion is killed by this dualizing procedure, but the moment you're torsion-free, nothing's killed, and your sheaf embeds in the double dual. Okay, and we'll see later this is related to Uhlenbeck's removal of singularities. This is the algebrogeometric version of it. Okay, and then reflexive is where E is E double dual. And you don't see this in codimension 2. You don't see this until codimension 3. So on a surface, reflexive implies locally free. And then, you know, the next guy, these are the guys which are least singular is locally free sheaves. All right, so reflexive. So this implies, let me see. So torsion-free, these guys have singularities in codimension at least 2. These have singularities in codimension at least 3. And these have no singularities. Any questions about this? This is just sort of what we were discussing last time. And in some sense, it's these 3 that are relevant to gauge theory. There are rather specialized gauge theories that see these kinds of things. Like, the things that Thomas and Alexander were talking about can be modeled by these sorts of things. But we're not going to discuss those because you voted not to. Right. Okay, so I'm going to recap this set construction, but using homological algebra. Okay, so remember what we were trying to do was construct, we had Z was codimension 2 and local complete intersection, but you could think of as smooth as an example. Okay, and we wanted to form an extension of the form O goes to E. So this was going to be our rank 2 vector bundle. Goes to L, turns to the ideal sheaf of Z, goes to 0. Okay? And we wanted to form extensions of this form, and eventually L would then be wedge 2 of E. And this would be a Cazal resolution, but we're trying to go backwards. So we're starting from the data of L and Z, and we're trying to go back. Okay? And we had this condition that L should be wedge 2 of the normal bundle of Z by a junction on Z. But I'm not going to impose that condition now. So we're going to see it arise anyway. Okay. So we're interested in forming extensions of, and I'll say this the wrong way again, is this correct? Of this by this. Okay. And they're going to be our way of producing rank 2 vector bundles from codimension 2 things. Okay. And so these are governed by this group called extensions from L tensor IZ to O. And we'll get a little bit of a feeling for this group as we go along, because we'll do some computations and so on. But for now, just accept there's such a thing. And there's a long exact sequence coming from a spectral sequence, which tells you how to compute this thing. And rather than deriving that, I'll just tell you what the terms are. Okay, so the first term is HOMS from L tensor IZ to O. H1 of this. Okay, so we'll understand this in a second. But the first thing to notice is that HOMS kill this singularity, this IZ. This is to do with back here. So e.g., IZ sitting inside its double dual is IZ sitting inside OX. Okay, so why is that? What HOMS from the ideal sheaf to OX are given by functions. And you might think, so there are clearly, any function gives me a HOM from IZ to OX, okay, by multiplication. You might think there would be more. You might be able to take some functions with poles or something. But if you had a function with poles, it would have pole along a divisor. Okay, so it wouldn't be concentrated in Z. So it's basically Hartog's theorem. Any HOM from IZ to OX has to be just multiplication by a function. Okay, so away from Z, it's multiplication by a function, and Z is codimension 2 or more, so it's multiplication by a function globally. All right, so this is actually HOMS from this to OX is just HOMS from L to OX. Okay, so this is L dual. Okay, and we saw that last time. I'll briefly remind you what this is in a minute. And then there's another term, which are sections of local extensions. This is a sheaf of extensions. Okay, and then there's a boundary map to H2 of these HOMS again, which we said was H2 of L dual. Okay, so this comes from something called the local to global spectral sequence. but I tell you what the terms are and what they mean. Okay, so this term we've seen before, so at least away from Z, we've seen it before. So away from Z, so let me just point out, this is concentrated on Z. This is supported on Z. So why is that? These are local extensions between this sheaf and this sheaf. Okay, well away from Z, that's just extensions between a locally free sheaf and another locally free sheaf, and there aren't any locally. Okay, so locally, any rank 2 vector bundle is just trivial. It just splits. Everything splits. Okay, so locally, there are no extensions. So it's only on Z that you get extensions. So this is concentrated on Z. Okay, so away from Z, this just says that X1 is, this says that the extensions are H1 of L dual. Okay, and this is what we saw last time. These are just extensions between a locally free sheaf L and O. So we did it in Dolbeault cohomology last time. So remember in Dolbeault cohomology, the Dolbeault model was that topologically the extension is split. So you have O plus L away from Z. Okay. That's topologically, and you want to put a D-bar operator on this, which looks like the following. Well, O is a subsheaf, a holomorphic subsheaf. So it should still be sat there in the extension. So D-bar on O should just be sat there. Okay. So the image of O in this sheaf, is a section of it is holomorphic if and only if it's holomorphic as a function in O. Okay. The same is not true of L because L doesn't sit inside E, but we've chosen a non-holomorphic way of splitting this and seeing L inside E, so that isn't going to be holomorphic. So, but once you project back to L, it should be holomorphic, so you should get D-bar of L here. But then you're going to add a 0-1 form. So this would be sigma, where sigma was a 0-1 form going from L to O. Okay? And then when you square this, you get D-bar squared is, okay, well we know that O is holomorphic, so D-bar squared there is 0. D-bar squared here is 0 because L is holomorphic. I get 0 here, and here I get this D-bar applied to this sigma. Okay? And then for this to define an integrable holomorphic structure on E, I need this to be 0 by the Newland and Nuremberg theorem or whatever. Okay, so I need D-bar of sigma. This is the integrability. Okay, so away from Z, we end up with elements of this cohomology. Okay, and you can look at gauge transformations and you see that you divide by the exact. Dividing by gauge transformations gives you dividing by the exact guys. All right, so these are the so more generally over Z, these are the extensions. Right, this in a different color. So these are the equisingular. No, let me come up with that word later. Let me say these are the locally trivial extensions. Okay, more globally. So these are the ones that. So extensions which look locally like just 0, so just the direct sum. But globally, they're twisted in this way. All right, so they sit inside the extensions, but then there's this map to here, and this takes an extension to its local part. So I ignore this global twisting, and I just see locally what does this extension look like. So in order to understand this, we have to compute this sheaf here. All right? So how do we compute? And I do apologize for doing such computations, but that's what you asked for. So let's compute this. Okay. So how do we compute such a thing? Well, what we're supposed to do is resolve x is the derived function of Hom, whatever that means. But what we're supposed to do, what the recipe is you replace this nasty-looking sheaf, which doesn't behave well with respect to Homs, by something which does. And that would be a locally free sheaf, because that's locally, it's a projective module. Okay, so what you do is you resolve this by locally free sheaves and then compute Homs. So how do you do that? Well, we already know locally how to compute this. Okay, so this is a sheaf, so I can compute it locally. And let's do so by resolving Iz, or L tensor Iz. I mean, L is locally trivial anyway, so I won't bother too much about L. So how do I resolve Iz? Well, we know how to do this, by the Cazal resolution. Okay, so we can say locally, at least, we do have such a Cazal resolution. We don't know globally yet. We're going to worry about that in a second. But we do have a local Cazal resolution. Okay, so locally, by looking at just the two equations cutting out Z, we take the Cazal resolution of that, and that gives us something like this. Okay, I'm sorry I haven't changed letters, but it gets all, maybe I could call this an F. Okay, where F exists locally, maybe not globally, but where F restricted to Z is the normal bundle to Z. Okay, that was the adjunction we discussed last time. Okay, and then there are lots of choices of F, but it doesn't matter. The final answer will be independent of that. Okay, so what we do is we say, well, this nasty-looking sheaf, we replace it by this nice-looking sheaf, and instead of applying Homs to this, we apply Homs to this. Okay, so the recipe for X is you say the Hom complex, which is called, this is like the chain complex, which is going to compute X. This thing's called R Hom. Don't be intimidated by the notation. From wedge to F, tensor Iz to Ox is, what you do is you replace this by this. Okay, so these two are what's called quasi-isomorphic. This complex of sheaves is injective with co-kernel this, so I replace this by this quasi-isomorphic complex here. So this is Homs from this complex here. O goes to F to Ox. Okay, which is what? Which is, when I dualize this, I get F dual goes to O, tensor Ox. Well, yeah, I don't really need that. I just dualize each piece individually and the map. And there was this local section cutting out Z. So this is contraction with that section here. Okay. And then we recognize this as the dual Cazal complex that we discussed, or part of it that we discussed last time. This has kernel wedge 2 F dual. Let me just check I've got all this right. What am I resolving? Why did I end up with wedge 2? Oh, I see, because of this wedge 2. Yeah, maybe I didn't. Oh, never mind. Never mind. Okay. Kernel wedge 2 F dual and co-kernel. Right? This section goes on to the ideal sheaf of Z. inside O. So the co-kernel is O divided by the ideal sheaf of Z. It's the functions on Z. Okay, so this is the HOMS. The H0 of this complex is the ordinary HOMS from here to OX. And this is the first cohomology of this complex. This is the X1s. All right. So the upshot, if I remove this twisting by wedge 2F, is that, so the upshot is, of this computation, is that HOMS from IZ to OX, so I've removed this wedge 2F here, that removes this wedge 2F here. These are just OX, well we already knew that, and X1s, IZOX, are wedge 2 of F dual, but remember restricted to Z. F restricted to Z is the normal bundle. So this should be, is it the normal bundle or it's dual? I feel like it should be that. Yes, that's correct. Okay, so this uses the fact that F restricted to Z is the normal bundle. Okay. So I picked this extension of the normal bundle, this F, but the answer is independent of it. Okay, and this all patches together. Okay, so this is just true. You can forget the derivation now. All right.
That's a line bundle tensor Z.
Yes, sorry, yeah, that's right. That's kind of notation. So maybe the correct way of saying it is the push forward, where All right, so if I go back to here, we now know what this is. This is H0 of L dual tensor that guy. L dual tensor wedge 2 normal bundle of Z. Okay. And, you know, pushing forward doesn't change sections, more or less doesn't change the sheaf. So I compute this on Z. This is a sheaf on Z. Now, the case we discussed last time was where L restricted to Z was wedge 2 of the normal bundle. So, e.g., if L restricted to Z is wedge 2 of the normal bundle, then we get X1 goes to H0 of OZ goes to H2 of L dual. All right. And then sort of 1 in here is what we called delta Z last time. Or maybe we call this its image in here. All right. And we described this map here. This was the map. This map was easiest to describe by its Serre dual. Okay, so we go the Serre dual of this is Hn minus 2 of L. Let me write it here. And the Serre dual of this is Hn minus 2 of the canonical bundle of Z. All right? And this is just the map which restricts to Z. All right? When you restrict L to Z, let's hope I got this right. I didn't. I missed Kx. Okay. So when you restrict L to Z, you get wedge 2 of the normal bundle of Z. Okay, so you get the normal directions to z. When you contract those with all the covectors on all of x, you end up with just the covector, the canonical bundle on z. Okay, so again, that's a form of a junction. Okay. So now, what does this 1 correspond to? This corresponds to the local extension. Well, we just computed it here. It's this one. Maybe up to twisting by this wedge too. Anyway. That's more or less a tautology. If you follow it through, I mean, tautology is always impossible to explain. So, but that's a tautology of how we computed x. We computed it from this extension. Okay, so 1 corresponds to this extension. Okay, and that's locally free. Okay, whereas 0 corresponds to the trivial extension, which would be O direct sum, whatever. What did we do? Was it L? L tensor I, Z. That was the one we didn't want. All right, so what we're looking for is a global extension which gives that 1 locally, or some non-zero multiple of it. Because that's what gives me something locally free. If I choose a global extension which gives me 0 on z, then I'll end up locally just with this direct sum, this rubbish extension, which is singular. Okay, so locally free extension corresponds to something in here which maps to 1 here, or maybe z's disconnected, in which case it should map to element of x1, which maps to, let me say, AI, where Z is disjoint union of a bunch of ZIs, okay? So here, where each AI is non-zero. All right, so if it's non-zero, then you get a locally free extension. If it's 0, you get a singular extension, a trivial extension locally. Okay, so i.e., I want to choose AI whose boundary map is 0. Such that the boundary of all these AIs is 0 in H2 of L star. Or, which was this H n minus 2 L tensor k x dual. Okay, so I want to choose points with coefficients, non-zero coefficients, such that all those points give you linear functionals on here by taking these guys, restricting them to z and integrating. And you want to know that the overall linear functional is 0.
So in small open sets, we get non-constant local extensions in OZ, which might be 0 at some points.
Yes, so I'm going to come to those in a second. Yeah, but first I'm going to do surfaces. So e.g. x is a surface, so that these z's can be disconnected. Okay. Now then, we have z is a bunch of pi's, a bunch of points. L is arbitrary. Remember, I keep asking for this L to be an extension of the wedge 2 of the normal bundle of Z. Well, in that case, any L is an extension. You can pick an isomorphism from L restricted to the PIs to the wedges of the tangent bundle of S at PI. Okay, so L is arbitrary. Okay, and I want to find these AIs. Sorry, these are the class of the points, of course. Okay, such that some AI delta PI in is 0. And I want all the AIs to be non-zero. Okay, so that's rather easy to do. If I choose enough points, right? So if I choose, the number of points to be bigger than the dimension of this group, or what was this group? It was H2 of L dual. Okay. Then the linear functionals they correspond to so I'm just going to swamp this group here by a whole bunch of linear functionals. There must be some relation between them. Can't be linearly independent, so they have some relation. Whoops. Okay, so I just take too many of them, such they can't all be linearly independent in here. So I get some AI delta PI 0. Okay? So now I throw away the PI with AI equals 0. Okay, if I don't do that, what I'll do is I'll end up with an extension which has some singularities at those points. I can also do that. Okay. And so we get what we want. All right? We get these non-zero AIs such that this relation holds, and so we get an extension with E locally free. And then we can also make it stable. And so it'll have an anti-self-dual connection on it by the Donaldson-Uhlenbeck-Yau theorem. And how do we do that? So pick L to have degree positive with respect to some Kähler form or hyperplane class. Okay, so that means that the degree of E is positive, and it means this section here doesn't destabilize it. Okay, but maybe other line bundle, because E is rank 2, in order to check whether it's stable, I only have to check whether it has sub-line bundles. Okay, so now I want HOMs from curly L. This is a different line bundle. Sorry, M always seems wrong for a line bundle. So curly L to E equals 0 for all curly L line bundles with degree L greater or equal degree E over 2. What was the other thing? I can bound them at both sides. And so why is that? You see, if degree L was less than the degree of big L, then there couldn't possibly, no, then it wouldn't destabilize. What do I? Sorry, if degree L was bigger than the degree of straight L, then there couldn't possibly be any HOMs. Because the degree of this is bigger than 0, remember? So if this degree of L, curly L was bigger than the degree of big L, straight L, which is positive, then there couldn't be any HOMs from L to this, because L would be too positive, and you can't have HOMs from positive line models to negative line models, and there wouldn't be any HOMs to this for the same reason. So this is all you have to check here. Okay, so that's just an obvious computation. Okay, so how do we stop this? So pick such an L. How do we stop this? Well, we can check these HOMs from our exact sequence down here. Okay, so tensor that with the dual of L. So we get 0 goes to L dual, goes to L dual tensor E, goes to L dual tensor L, tensor the ideal of the points. Okay, so now we can take sections. So when I take sections of this, these are the HOMs from L to E. Curly L. Okay, and then these are sections, and then we carry on to H1 of L dual. Okay. And we're trying to show this is 0. Okay? This is 0 because of the degree of L is this 0? Yeah. The degree of L is positive, is it? Yeah. Degree of L is bigger than degree of E over 2. So the degree of L is positive, so the degree of L dual is negative, so I can't have any sections. Okay? If I had a section, that would vanish on a divisor with negative degree, which is a negative volume. Which is not possible. Okay, so this vanishes. So it's enough to make this vanish. So how do we make this vanish? Sorry. Where?
The thing you just pointed at.
Yeah. Oh, these, I missed some tensor products.
Oh, that's a tensor product of all
Yeah.
the things,
Yeah. Okay. But we can easily fix this by, choosing our points correctly. So we can kill this as follows. So consider this. This is some fixed vector space. Okay, so I can pick a section, non-zero. Okay, that vanishes on a curve, and then I can pick P1 to not be in the curve, to be in the surface minus the curve. All right? And what does that mean? That means that this in here has codimension 1. Okay, because my point, if my sections are to vanish at P1, then I can't include this section S1, so it's missing S1. All right? So I can choose my point to impose a condition on this linear system, is the way an algebraic geometer would say. Okay? And similarly, so repeat. If I start with a section S2 of this guy, and now I pick P2 in S, take away S2 inverse of 0, etc. Okay, so I can choose my P2 to also cut down by 1, and so on and so forth. Okay. Inductively, eventually I choose, so if the number of points is bigger than the dimension of this L dual tensor L, I can choose them. Such that H0 L dual L IPI is 0. Okay, so I just cut down by one dimension each time. Okay, so this implies that. Yeah, the ideal sheaf of all the PIs. Yeah, sorry. Okay, so I end up from that exact sequence with HOMS from L to E equals 0. All right, so I've done it for one line bundle. You can do it for many, and the line bundles satisfying this condition with non-zero sections of this form a bounded family. And so anyway, one can do this locally and then patch together. One can do this for all L's. Okay, I just did it for one.
Even if S has done that group, so
yeah. So you do it for one line bundle, and that does it for all nearby line bundles in the Jacobian. And then you do it for another, and you eventually cover the Jacobian. In fact, on a Zariski open of the Jacobian. So now you can pass to a divisor of the Jacobian, do it again. You keep cutting down the line bundles which cause you problems. So after a finite number of steps, you can make. So eventually, by appropriate choice of the PIs, E becomes stable.
So where does degree L bigger than AE over 2 go?
Well, if it wasn't, you wouldn't have to worry about it because it wouldn't is that what I wanted?
it doesn't have any finite name plus or minus.
That's what I thought. So is that where it gets used?
Is that where it gets used? Yeah. Yeah, that's right. You couldn't do it for very, very negative curly L's because you will always have HOMS from very negative line bundles to your E. And you don't want to, they don't affect stability, so you don't care about that. Yeah, so it's to make this a bounded family. The set of curly L's which satisfy this inequality and have non-zero space of sections here form something called a bounded family. It just means you can control it. Okay. Okay, so in this way you can produce stable bundles, so anti-self dual or Hermitian-Yang-Mills connections. And then, so just to relate to Ben Sibley's talk, I just say very briefly that, if I turn off some AIs, so I use sort of T times AI, where T is in some parameter space. Let's say the complex number is parameterized by T. And then I send T goes to 0. Okay. Then what I get is extensions ET, which you should think of as anti-self-dual connections or instantons, tending to some E0. But E0 will have some of the AIs 0. Okay. So this will no longer be locally free. So locally, near some of the PIs where the AIs, I've turned them off, it looks like the trivial extension. Okay? Well, locally L's trivial anyway, so it looks like this. All right. And so this is called a bubble in instanton language. So I've arranged my, I'm assuming I'm turning off my AIs in a clever way so that the stair construction works at every stage. I can form this extension, and also I preserve stability. So let's assume also that this is stable. Okay, so then this is the bubble, and this corresponds to, so Uhlenbeck tells you, can remove the singularity. And what does that correspond to in algebraic geometry? It corresponds to taking the double dual of this. So that means take the double dual. In other words, just take O plus O. And then she would also remember the point where the bubble occurred. So the map in Ben Sibley's talk would take this sheaf to this. Okay. So this is locally, right? Globally, it's some stable sheaf. Globally, this would be unstable, so this wouldn't be an instant top. But locally, this is what it looks like.
But you've lost some information.
Yes. So this is the map from, the Giesecke moduli space to the Uhlenbeck moduli space. And so this contracts the following information. I can't reconstruct this from this. So in this particular case, suppose I'm just at one point, pi, this contracts a P1. And what is that P1? That's up to scale, that's the surjections from the double dual to OPI. Okay? In other words, I can construct this by taking it as the kernel of a map from of this map, right? So given the Uhlenbeck data, so I take a nice vector bundle, a reflexive sheaf, which is therefore a vector bundle because I'm on a surface, and this point, this bubble, I can recover my sheaf back here from this exact sequence. So I need to take a surjection to OPI, and then I take the kernel, and that'll be this. All right? So, but there's a whole, at the point PI, there's a whole family, P1 of such surjections, and they all get contracted in this map. Okay? So you lose some information passing from Giesecke to Uhlenbeck. Okay? So the direction, in Giesecke, you remember not just where the bubble is in space, but also in the fiber direction, in the vector bundle. Okay, and so this gives the local model in 3 folds as well. So yeah, let's go back to, oh, that took much longer than expected, sorry. Okay, so let's go back to 3 folds. Okay, so in codimension 2, the model is, surface times by C or something. Okay, so we can have rank 2 bundles with sections, extension with zeros, a curve because that's going to be codimension 2. We get some kind of extension. Okay, and if locally we turn off the extension, we get a bubble along C. Okay, so for differential geometers, that's very familiar. But now what happens in codimension 3 is completely different for 2 different reasons. So one is what Dominic pointed out earlier, which is that I needn't now globally have that this L is the restricts on the curve to the determinants of the normal bundle. So now, such extensions, remember, were governed by X1, L tends to IC, goes to OX, and these had this, so this was these are the local extensions, and this was sections along C of L tensor wedge to the normal bundle to C dual. Okay, and then they map to H2 of L dual. I didn't really tell you what this map is. Maybe I'll just say it in words. This says if I take a local extension, then I know locally what my extension looks like everywhere. And I know that on overlaps, my 2 descriptions will be isomorphic, but not canonically. So when I try and glue them, I can get a co-cycle on triple overlaps, where the gluings don't agree, and that co-cycle lives in here. Now, I've, until now, been concentrating on the case where this is the trivial bundle, so where L restricted to C is isomorphic to wedge 2 of the normal bundle of C. Okay. But we can have a different situation where L restricted to C has more positive degree than this guy. If it has less degree, this will be 0, and all the extensions, there won't be any locally free extensions. But I can have the situation that if the degree of L restricted to C is bigger than the degree of wedge 2 of the normal bundle to C, okay, I can get, then there may exist sections of H0, X1 with zeros on C. Okay, so these correspond to extensions which are locally free away from the zeros, but are merely reflexive over the zeros. And that example I rushed through last time, I was going to do it again, but God, this lecture's taking much longer than I expected. Sorry. That came from this behavior. It came from an extension which had a 0. If you remember, I had 2 curves like this in P3, and I formed a bundle from them. And then when I moved the 2 curves together, the determinant of the normal bundle changed, and that meant that when I formed the extension here, I got a reflexive sheaf, and the explanation, which has different third Chern class, and the explanation was that the limit of these curves was not this curve, but this curve with a little embedded point. And that meant that the limit of these bundles was not the reflexive sheaf, but the reflexive sheaf with a point removed, which made it non-reflexive. Okay? And so
stable or not?
you can make them stable, yeah. They were just local models, but yeah. I hadn't thought about that. The particular thing I did in P3, I haven't thought about whether it's stable. Okay. But more generally, one can have this behavior where you either get bubbling along a curve, and the curve can have singularities, or this kind of horrible embedded points, or you can even have no bubbling, because I choose a non-zero extension here, so I get a locally free sheaf, but I still get singularities in codimension 3. Okay, so you can still have the situation where you have everything looks like a nice vector bundle with no bubbling along curves or anything, but then suddenly you get these singularities in codimension 3. All right, so let's see what I can do in 5 minutes about talking about those reflexive sheaves. Okay, so reflexive sheaves. In dimension 3. So, you know, in general, I'll have some kind of torsion-free sheaf sat inside a reflexive sheaf. So this would be torsion-free. This would be reflexive. And then this will be something zero-dimensional, e.g. the structure sheaf of a point. So the sheaves you might be interested in that will come up in gauge theory might look like this guy, but they can be described in terms of their reflexive hull plus some of these codimension 3 bubbles that are not so well understood. But I just study, well, mainly I'm going to study these guys rather than these guys, but you could, given one of these guys, you could ask, can this be smoothed to a vector bundle? Okay, so those examples I gave last time could. This never can, because if it has reflexive singularities, then they all contribute positively to the third Chern class. So obviously you can't smooth that to a rank 2 vector bundle, because that would have 0 third Chern class. So the standard example of a reflexive sheaf, so the simplest possible example of a reflexive sheaf is on C3, a local model is just you take O, goes to, via X, Y, Z, the usual coordinates on C3, and you take the co-kernel. Maybe I'll call it curly because it's a sheaf, it's not locally free. Okay, so away from the origin, this is clearly rank 2, but then at the origin, this is reflexive. And what I was going to mention very briefly is sort of Simon's program for understanding these sheaves and understanding whether these sub-sheaves can be smoothed via deformation to the normal cone. So what Simon would say is blow up. So this is at P, which is the origin. So Simon would say blow up at a point, blow up X in P. So this is the local model, but you might have a global situation. Pull back your sheaf. Divide by torsion. Because it does nasty things, this pullback. It'll introduce some torsion. Divide by torsion. Okay, and this gives you a new sheaf. Now, blow up X times C in P times 0. This gives you a new sheaf, E bar. So maybe a picture is as follows. Here's your copy of X. Here's a point P on it. And then this is C down here. You blow up in this point here. That introduces an exceptional divisor. So this is a copy of X, this is a copy of X. This is the blow-up of X in the point P with a P2 exceptional divisor. Okay, and glued to that is a big P3. That's the exceptional divisor of the whole blow-up of the whole fourfold X times C. Here's a copy of X again with the point P. And then you can follow this point P, and it goes to some point in the P3. It doesn't go to a point in this P2. Okay, so there's a new point P, which is sort of the proper transform of the old point P. Okay, and you get this new sheaf on here, which you can restrict to this central fiber. And so oops. So e.g., if I start with this E, so if I start with the co-kernel of O goes to C3, what do I end up on that P2 or that P3 there? Then when I pull back, X, Y, and Z vanish on the whole exceptional divisor. Okay, so I can divide them, and this is a divisor. Let me call this. Of course, I want to call it D for E for exceptional, but I can't use E, so I'll call it D. Okay. So what I can do is I can divide by the section which vanishes on D, the section of O of D which vanishes on there. So what I can do is I can form upstairs. I can look at X divided by SD, Y divided by SD, Z divided by SD. And that's the section of O minus D plus 3. And I can take the co-kernel of this, and then I don't have time to explain why this is this recipe, pull up and divide by torsion. But it's not hard. Okay. And so, in particular, this is E bar. So, in particular on P2, on restriction to that P2, what do you get? You get O goes to O1, 3 copies. Okay, and then this is just the standard map. This is the Euler. So from the Euler sequence, this is the tautological map. If you twist by O minus 1, it's O minus 1 sat inside the vector space that P2 is made out of, is the projectivization of. So this is a tautological map. And so the co-kernel here is the tangent bundle at P2. Okay, so this is E bar restricted to the P2. And this is what Simon would, I presume, called sort of the link of E. All right? And E bar restricted to the whole P3 would be sort of something like the tangent cone of E. And the question that Simon has is basically, can we modify the extension of this TP2 here to get something locally free over P3. All right. So one can do this to any sheaf, a reflexive sheaf or some subsheaf of that reflexive sheaf. One can do this, then say, can I modify? I want to modify it at the singular point. So I blow up the singular point and instead try and modify it over this whole P3. If I can, I get a nice locally free sheaf on that central fiber, and then, although you may not believe it if you're not an algebraic geometer, deforming that to nearby fibers is extremely easy. That's a well-studied problem. We know whether we can deform it to nearby fibers. But this is the hard problem. To know whether we can smooth a sheaf is to know whether this sheaf here extends to a locally free sheaf over P3. Okay, so in the TP2 case, this is well known not to extend to a locally free sheaf over P3, essentially because this map here always has zeros on P3. It doesn't have zeros on P2, but it always has zeros on P3. And so you can see here that you can't smooth this example. But I was going to do, well, I ran out of time. So I was going to do, it's easy to see in the examples that I created by the Serre construction with those curves, this nasty sheaf that you get from this curve here. You can see using this construction very easily how you can extend it to a vector bundle over P3 just from its data on P2. More or less because what you end up with in P3 is a picture like this, and on P2, so this would be P3, this would be the P2 boundary. On P2, all you end up with is the 2 points of intersection of these two curves. And what you do is you ask that the sheaf, as you extend it over P3, you don't take this extension that you started with, you take a different extension where basically these points, you head them off in a slightly different direction. So not in the original directions which intersect, you head them off in a different direction and you can make these two curves not intersect. And that's how you end up with a bundle which extends over P3 and is really locally free. And you can encode all this in various cohomology groups. So these extensions of this bundle on P2 to the first order neighborhood of the P2 in the P3, and then higher order neighborhoods. But the extension to the first order neighborhood is governed by this group. And I was going to explain how you compute this and where you see this, and what you have to divide by to see. You don't want extensions which differ by automorphisms of P3 and therefore give you something isomorphic. So you end up dividing by the tangent space to X. But anyway, I ran out of time, so I won't explain this. But people who are interested in this and have heard Simon talk about it but want to understand it better, please do ask me and I can explain where all this comes from. Okay. Yeah, sorry to run over.
Question for Richard.
So this whole program a way of deciding which rank 2 reflexive sheaves are kind of smoothings of vector boxes?
Not the reflexive ones, yeah. They would be the hulls. That's like you've removed. Yeah. It's a bit like you've removed the codimension 3 singularity, but you've left in some remnant of it. So yeah, but that's right. So it's the whole program to find which sheaves. Let's say it this way. The easiest thing is you say which sheaves which are locally free except in codimension 3, but do still have maybe C3 equals 0. Which of those arise as limits of locally free sheaves? And they all sit inside some reflexive hull. It's double dual. And you can study that, and then you can also study its quotients by dimension 0 sheaves, and those are the original sheaves. So yeah, it's asking which of the original sheaves are limits of vector bundles. And all I can tell you is where you get this group from and so on, and then one has to study it in examples. I don't have any decent answer to that question of which sheaves are limits of vector bundles.
Did I understand correctly? Your example with the two lines in
Yeah.
free,
Yes.
when they intersect, the sheaf you get as a limit is no longer torsion-free, is it?
It's torsion-free, but it's no longer reflexive. That's correct. Yeah, yeah, yeah. That's right. And its reflexive hull can be described in terms of this limiting curve by doing the Sayre construction on this limiting curve.
And of course, the reflexive hull will have a higher C3.
Yes. And that is because initially, when we had this curve, our line bundle that we chose had the property that its restriction to this curve was the wedge 2 of the normal bundle. But in this curve, the wedge 2 of the normal bundle is different. Essentially because, these were linear, so they were cut out by hyperplanes. So their normal bundle was O1 plus O1. This is given by one hyperplane, the plane that it lives in, plus then a quadratic. It's given by x times y equals 0. So this point here adds a kind of pole to the description of the normal bundle. And that means the normal bundle is O1 plus O2 here. So when we do the Sayre construction with this local section of the X1 sheaf, we get a 0 at that point, and that's what makes a reflexive sheaf. And then the way we kill that is by putting in this extra point, which we remove from the sheaf. And then we get this non-reflexive sheaf, which is the limit of these vector bundles.
More questions for Rick?
Can you clarify something you said about rank 2 and rank 3? So I might have misheard, but did you say that whenever you form a codimension 3 singularity, you have to have, that gives you a positive third chain pass?
Yes.
So those singularities can't form if you're just looking at rank 2.
No, so that's right. Your rank 2 vector bundle could not degenerate to something reflexive. So it has to go to something non-reflexive. But its reflexive hull, so its double dual, sorry,
Right, okay.
would then still be a reflexive sheaf with non-zero C3. That's absolutely fine. Yeah. Yeah.
Is deformation problem when you start with the central fiber and you want to deform it to a
Yeah.
briefly sheet? Can it happen that you must deform also the Palladius structure?
You want to deform X as well?
Right, because the index is 0.
There's the deformation problem. I mean, that's right. So if you start with a vector bundle, if your vector bundle's transverse is isolated, if its X2 is 0, then the deformation automatically exists. You don't need to deform the Calabi-Yau. That's right. So in general, if the vector bundle you produce by gluing, a bundle, the bundle you already had on the blow-up of X to this bundle that you managed to extend from the P2 over to the P3, when you take that bundle, if its X2 is non-zero, so if it's not an isolated point, or it's not transverse in the moduli space, then you would have to work harder to get it to deform nearby. So you might have to deform the Calabi-Yau or something. But if you can control its X2, then immediately So if the bundle you started with was an isolated bundle, which is meant to be the generic situation, you'd be absolutely fine. It would deform. There would be no obstruction.
Any other questions for Reggie?
Thank you.